The first paper that we are going to see is, as I announced, it's from Japan, it's from Tokyo. The main author is Tom Taylor, whom I met personally last year in Tokyo, and I was really happy to chat with him about the process that he was working on, and I'm really happy to see his paper now here in the schedule, which is entitled Evaluation of a Concept Out-of-Autoclave Process for Manufacturing Carbon Fiber Reinforced Polymer Automotive Parts. The co-authors are Mr. Zhang and Mr. Yanagimoto. So thanks for submitting the paper. Thanks for preparing the presentation. We are really looking forward to that. Thank you.
Hello everyone. Welcome to our presentation, Evaluation of a Concept Out-of-Autoclave Process for Manufacturing Carbon Fiber Reinforced Polymer Automotive Parts. My name's Tom Taylor. Co-authors are Zhang and Professor Yanagimoto from the University of Tokyo, and this research funded by the Japan Society for the Promotion of Science. Okay, let us start with a brief introduction. So CFRP, specifically here I'm talking about thermoset-based matrix CFRP. This first applied to automotive in the early 1980s with Formula One racing cars. As with most technologies in the automotive sector, begin in F1 and then gradually filter down towards production vehicles. And this is the path that CFRP is trying to take. And the reason for that is for lightweighting. So CFRP, amongst other attractive properties, is characterized by very high specific stiffness and specific strength, and therefore for any structural application where low weight is desirable, then CFRP is a very useful material. So with internal combustion engine powered vehicles, the lightweighting is very important for the reduction of fuel consumption and in turn the CO2 exhaust emissions. In terms of electric vehicles, then one of the problems with electric vehicles is limited recharge range. If we can reduce the vehicle weight, then we can increase the recharge range. So these are some of the reasons why CFRP is useful in mass-produced vehicles. Now, this is an example of such a production vehicle, a medium volume produced vehicle, a BMW 7 Series, which is using CFRP. And what has made the application of CFRP to this production vehicle possible has been the development of out-of-autoclave part manufacturing processes. So CFRP traditionally produced through an autoclave process, which is very time consuming, energy intensive and labor intensive, and therefore not suitable for mass production, but gives rise to the highest quality parts. Now if we look at this slide, we can see that there's a trade-off between the part quality and the cost of manufacture. So the autoclave produces parts of the highest quality, but not suitable for mass production due to the cost involved. So the out-of-autoclave process is developed. These reduce the cost, improve applicability to mass-produced vehicles, but the quality of the part is impaired, and therefore applicability to the vehicle and the application it can be used within is therefore going to be limited. So this is our concept part manufacturing process, which aims to address that balance between the sacrifice of part quality and the cost. So we can consider this as a dummy metallic sheet assisted pre-preg compression molding process. So we start with our pre-preg material, we lay up into desired laminate configuration, sandwich between dummy metallic sheets, place in the forming tool, induction heat to the forming temperature, form into the part geometry, continue heating to the dwell temperature, then under the action of the heat and the tool pressure, we cure the pre-preg. We then deactivate the heating, initiate die cooling to cool the part down to near ambient temperature. Then we can remove the part from the tool and the dummy sheets can be re-rolled back to flat sheet and recycled through the process. So this process we have researched over the past 2 years. We have optimized many of the parameters In this research that we're going to discuss today, we're going to demonstrate applicability of this process for producing replica automotive parts. So, on to our experimental research. So in this research we used this laminate configuration. Our prepreg is of 0.1mm laminar thickness. We used 10 layers in this configuration, giving us a total laminate thickness of 1mm. Then we have our dummy metallic sheets constituted by aluminium alloy, and we coat the inside surface of our dummy metallic sheets with mold release agent before sandwiching around the prepreg. This is the part geometry, which we chose to produce a simple open box section geometry, and this was chosen as it's a simple replica of numerous automotive parts. So in terms of twist beam suspension systems, these are usually a U-bend or a C-bend geometry, not so dissimilar from our part here. In terms of crumple zones, longitudinal beams, such as this part here, this is quite similar to our geometry here. And in terms of the safety cell, tunnel reinforcement part, which is this part in the middle here, this is very similar indeed to what we have here. So this is our setup for forming. This is our upper die, our lower die, induction heating coil. This is our water cooling supply for water cooling of the die. Then we have our sample, our thermocouple spot welded to the lower surface of the lower dummy metallic sheet for temperature control. Our thermomechanical cycle, these parameters optimized in the previous research. Heating rate 2 degrees per second to the forming temperature of 150 degrees. Stroke displacement rate 1 mm per second to forming depth of 95% of the complete stroke displacement. Resume the heating rate of 2 degrees per second to the dwell temperature. When we reach the dwell temperature, we complete the final 5% of the forming. Dwell conditions 230 Celsius for 600 seconds, and then die cooling at 60 degrees per second. Once we formed the parts, we then conducted a range of mechanical tests to evaluate numerous attributes for automotive application. So the flexural testing, the tensile testing, and the fatigue testing, these were actually performed on flat parts. So the same method as shown on the previous slides, but we produced flat parts rather than formed parts for these three mechanical tests. The compressive crash box testing was conducted on the open box section parts as shown on the previous slides, and we have displacement rates of 1, 10, 100 millimeters per second, corresponding to effective universal strain rates of 0.02, 0.2, and 2 seconds to the -1. So let us see the results. So we managed to produce springback-free parts. If we look under the microscope, however, we can see some geometric inaccuracies. So we have areas of thinning in the corners, we have waviness to the surface profile, but these defects are probably the result of insufficient die design and refinement rather than problems with the process itself. However, here we can see non-uniform fibre alignment. Here we can see fibre fracture perpendicular to the bending crease of forming. These are more important and severe forming defects. If we look at the flexural properties, the flexural testing, so in red we have parts produced by our concept process, in blue we have benchmark parts produced in the autoclave process. In terms of the flexural stiffness, then the properties are quite similar between the two processes. Also, the flexural strain to failure is quite similar between the two processes. However, where there is a difference is that in our concept process we have greater plasticity to the parts. Now this would suggest inferior curing behavior during our concept process. Also, we can see that parts produced in our concept process have around 80% of the flexural strength of the parts produced in the autoclave. Now this could be related to the non-uniform fibre alignment and the fibre fracture, as we saw on the previous slides. In terms of the tensile testing, it's a similar story. Parts produced in our process have around 80% of the tensile strength of parts produced in the autoclave. In terms of fatigue properties, again, it's a similar story. So parts produced in the autoclave exhibited fatigue strength given a fatigue life of 10 to the 7 cycles of more than 731 megapascals. In our concept process, more than 646 megapascals. So these are the load displacement graphs from the compressive crash box testing. Now these graphs are a little difficult to understand initially, so let's break them down and look at some important properties. So here we are looking at 3 important properties. The crushed energy absorbed is the energy absorbed per crushed length. The specific energy absorption is the energy absorbed per crushed length per unit mass. And the crush force efficiency is the energy absorbed per crushed length per peak load. And then in blue we have parts produced in our concept process. In green we have parts produced in the autoclave. And we can see the first observation is that parts produced in our process exhibit superior properties to the autoclave. The second observation is that generally as we increase the displacement rate, each property increases. Now these observations can be explained by the deformation behavior. So we see that with the lowest displacement rate of 1 millimeter per second, we have a deformation mode of folding and bending which dominates. When we increase the displacement rate to 10 millimeters per second, we have a deformation behavior of fragmentation with fragmentation of material. As we increase the deformation rate to 10 millimeters per second, then we have a deformation mode of brittle failure, which is characterized by fragmentation and expulsion of material. And as we increase the displacement rate, what is happening is that the crushed length is decreasing, and as the crushed length decreases, then each of those properties that we saw on the previous slide is effectively increased. So that's the explanation for the trends that we see. So on to conclusions. So we managed to produce spring-back free parts with mechanical properties within approximately 80% of autoclave produced parts. The inferior properties from the concept process mainly attributed to non-uniform fibre alignment and fibre fracture during forming. But importantly, we believe that from our process we have made a significant step towards realizing the application of CFRP to the mass-produced automotive architecture. Thank you very much indeed. I welcome your questions.
Thank you very much, Tom Taylor, for doing the presentation. We are now trying to get him live on the phone in this session for the question and answer. Tom, thank you. We can hear you. Can you hear us?
Yep, I can hear. Hello, friends.
Welcome from Berlin to Japan. Thanks you for your paper. When having a look at the paper and the presentation, I wondered about the shear that is applied to the fibers during the forming process. Did you encounter shear effects of shear on the fibers?
Yeah, indeed. So an important factor behind the pre-preg compression molding process is to have free flow of the different lamina of the pre-preg, so you don't avoid the tearing and also the disalignment of the fibers. So what we did not present in this presentation, but what we researched previously, was the optimal forming conditions to have the optimal flow of the pre-preg. So here we investigated the stroke displacement rate. We investigated the number of strokes to the forming. So for example, forming maybe 25% of the depth and then pausing for a second before continuing, and so on. And most importantly, we investigated the forming temperature. And by optimizing these parameters, and the result of that is what we used in this presentation here, we can minimize the shear on the different lamina. We can minimize the voids in the resin, and also minimize the disalignment of the fibers. Although we can see that we still have some disalignment, so the problem is not completely fixed. But this is indeed one of the biggest drawbacks of the compression molding process.
Okay. Do you reckon that can be simulated?
Yeah, it can be simulated, but the simulation of the compression molding process is quite a tricky thing to do, because
yes.
It's a highly dynamic process where the material properties is continuously changing. So there is research going on, not in our lab, but there is other research I've seen into that. But that's quite a difficult thing to do.
Okay, thank you. Can you comment briefly about the project context in which this paper stands?
So the process which we see here, while this is quite useful in its own right for forming monolithic CFRP parts, which is what we present here, the bigger picture and the bigger aim for this process is actually to fit into another process which we are currently working on, and we will aim to publish a paper on this in the coming month or two, and that is a hybrid part manufacturing process where we combine the hot forming process of metal, which could be non-ferrous material, or in our case we are looking at press hardened steel, and we combine this process which we present here at the end of that hot forming process to produce a hybrid part.
Okay, thank you. Thank you very much for sharing these insights and these details. Thank you to you, Tom Taylor, to Tokyo.
Thank you very much for organizing, and thank you very much for having me on in your conference.
Yeah, thank you very much from Berlin. Goodbye.
Thank you. Bye-bye.
So this was the presentation and the question and answer for the paper entitled Evaluation of a Concept Out-of-Autoclave Process for Manufacturing Carbon Fiber Reinforced Polymer Automotive Parts, authored by Tom Taylor, Mr. Zhang and Mr. Yanagimoto. Thank you.